Hello everyone, this is my circuit. The objective of this project is to design a complete biomedical signal processing system which acquires a mic level sound output like heartbeat from a stethoscope and then filter and amplify the mic level input to a line level signal. The amplified output should then drive an 8 ohm 0.5 watt speaker, which includes the function of adjusting the volume of gain to the end user's liking. This is my circuit schematic. I'll be explaining it in their 4 stages and share about some troubleshooting that I've worked on with suggested improvement to the circuit design. Before entering stage 1, the input signal passes through capacitor C1 that acts as a coupling capacitor which blocks off DC signal and allows only AC signals to pass through. Using the reactance formula, it can be explained. The formula to find reactance of a capacitor is given by Xc equals to 1 over 2 pi Fc. As the frequency at DC signal is nearly 0 Hz, taking the limit of reactance as F approaches 0 Hz, reactance will be towards infinity. This means that a capacitor will act as an open circuit. In comparison to DC signal, frequency at AC signal is high. Taking the limit of reactance as F approaches infinity Hz, reactance will be towards 0. This means the capacitor will act as a short circuit. Moving on, our resistors R5 and R6. They form a voltage divider which provides a DC offset for the input signal as the op-amp uses a single rail supply without voltage divider. Without the voltage divider, the AC signal will be at ground, which causes the negative half cycle of input waveform to be clipped off. With a voltage divider, the AC input will be shifted to 4.5 volts, which is half of VCC, where there will be no distortion. This allows maximum amplification of AC signal without distortion. At stage 1, it uses a TL072 IC. It is a low-noise, high-speed JFET input operational amplifier. This IC contains 2 op-amps, for which IC1A in stage 1 is configured as an active bandpass filter. It is a combination of active high-pass filter and active low-pass filter connected in series. In this case, resistor R2 and capacitor C2 form low-pass filters which determine the high cutoff frequency FH. Therefore, the low-pass filter can be calculated by 1 over 2 pi R2C2. This gives us a value of 1.064 kHz. Resistor R3 and capacitor C3 form a high-pass filter, which determines the low cutoff frequency FL. Thus, the high-pass filter can be calculated by 1 over 2 pi R3C3. This gives a value of 16 Hz. Then, we can find the center frequency by the formula square root Fc2 times Fc1. This gives us a value of 130 Hz. Altogether forms the bandpass filter connected to a closed-loop non-inverting op-amp. To find its voltage gain, the given formula AV equals to 1 plus R2 over Rin can be used. It will be then 1 plus 220K over 10K, which gives a gain of 23. Finally, the capacitor C4 also acts as a coupling capacitor which blocks DC voltage, only allowing AC signal to pass through the next stage. To set up stage 1, connect the positive terminal of the power supply to VCC of the breadboard and connect the negative terminal of the power supply to ground of the breadboard. Then, connect the positive terminal of the function gen to the positive side of the capacitor C1 and then negative terminal of the function gen to ground. For oscilloscope connections, connect the channel 1 probe to TP1 and channel 2 probe to TP2 and connect both black clips to ground of the breadboard. Then, set the power supply to 9V. Set the waveform of the function gen to sine wave and it should be set to high impedance mode. Then, set frequency to 1 kHz with 200 mV peak to peak. Now, switch on power supply and then press the output button of function gen. The 2 AC waveforms at TP1 and TP2 are as shown. The waveform at TP1 is 200 mV peak to peak, while at TP2, the waveform is at 3.36 V peak to peak, with the frequency set to 1 kHz. After measuring the filter's gain at different frequencies, we get this table. As the frequency increases, the filter's gain increases to a maximum of 23 at 100 Hz. Beyond 100 Hz, the voltage gain attenuates. From the table, we plot the frequency response curve. The passband gain of 23 is equal to 27.23 dB. The AV cutoff is minus 3 dB from the passband gain, which then gives us 24.23 dB. The 2 intersection points between the cutoff line and curve determines the higher and lower cutoff frequencies, which are estimated to be 1.2 kHz and 16 Hz. The bandwidth of this filter is calculated by FC2 minus FC1, which is equals to 1.2 kHz minus 16 Hz, which gives us a value of 1184 Hz, which is closer to the calculated bandwidth of 1.048 kHz. The Q factor can then be calculated by the given formula center frequency divided by bandwidth, which gives us 0.124. Since Q factor is less than 10, it is a wideband bandpass filter. This wideband bandpass filter is selected with its frequency range because it is used to detect the hard sound which ranges from 20 to 1200 Hz. In stage 2, IC1B shares the same TL072 IC with the first stage. IC1B is an op-amp configured as a closed-loop inverting op-amp. For this op-amp, the output signal is feedback to the input with a 180-degree phase shift. This means that when the input signal of a sine wave during a positive cycle is being applied to the negative terminal, the op-amp inverts it during the amplification, which results in the output corresponding to the negative half cycle of the input sine wave. Resistors R9 and R10 form a voltage divider like resistors R5 and R6 with a similar function. The formula for the voltage gain of closed-loop inverting op-amp is negative RF divided by Rin. When it's subbing in, AV equals to negative P1 divided by R4. Since the voltage gain is negative, it proves that the output is 180 out of phase with the input. With the trimmer put in place, the voltage gain can be adjusted by turning the trimmer to get the desired output, which is 5 VPP for the later stage. To set up stage 2, we will use the same function gen and power supply with the connections being intact. For the oscilloscope connections, connect channel 1 probe to TP2 and channel 2 probe to TP3, and both black clips should be connected to the ground of the breadboard. Switch on the power supply and press output of the function gen. We can control the voltage gain by adjusting trimmer P1, and we get a favored voltage of 5V peak-to-peak at TP3. By looking at the waveform visually at TP3, it is 180 degrees out of phase with the waveform at TP2. In stage 3, the output from stage 2 is applied to the coupling capacitor C5. Capacitor C5 has the same functions as capacitor C1 and C4, which blocks DC voltage and only allows AC signal to pass through. The op-amp in IC2A is configured as a Salient Key Design second-order low-pass filter. Because the op-amp is powered using a single-ray supply, the voltage divider resistors R11 and R12 is required to provide the AC signal with the DC offset of half VCC. This is key because it prevents distortion. Moving on, resistors and capacitors R8 and C6, R7 and C7 form two pairs of low-pass networks. Therefore, it is a second of the low-pass filter. To find the cutoff frequency, we need to use the formula FC equals to 1 over 2 pi square root R7 times R8 times C6 times C7. After subbing in the values, it gives us the value of 1023 Hz. Lastly, the coupling capacitor C8 will filter the signal, which will remove the DC offset voltage and only allow AC signal to pass through the next stage. To set up this stage, for the oscilloscope connections, connect the channel 1 probe to TP3 and channel 2 probe to TP4 and the two black clips to the ground of the breadboard. The other connections remain the same. To test how different frequencies affect the voltage gain of the filter, set the function gen to 100 Hz. So, at 100 Hz, the voltage gain at both TP3 and TP4 are the same, which is 5V peak to peak. Therefore, we can say that we achieved unity gain. Now, we will change the frequency to 1 kHz, and now at TP4, the frequency is decreased to 3.8V peak to peak. The Vin at TP3 remains the same. Thus, we can conclude that the voltage gain of the filter has decreased. Lastly, let's set the frequency to 4 kHz. At TP4, it is 180 mV peak to peak, while the Vin remains the same at TP3. After measuring the filter at different frequencies, we get this table. We can see that as frequency increases, the filter remains at unity gain until 100 Hz, and beyond 100 Hz, the voltage gain attenuates. We will then use this table to plot the frequency response curve. Unity gain is 0 dB. The AV cutoff is minus 3 dB from the passband gain, which is negative 3 dB. To find the cutoff frequency, it is the intersection points between the minus 3 line and the curve, which is approximately 1.2 kHz, which is close to the calculated value of 1023 Hz. Since the lowest frequency that can pass through is 0 Hz, the bandwidth will be equal to the cutoff frequency. To test how the trimmer value affects the AC signal at both TP3 and TP4, we set the frequency of function gen to 100 Hz and keep the other connections intact. Then, switch on the power supply and the output of the function gen. Since the filter is at unity gain at 100 Hz, we can see that V in and V out are the same value. By adjusting the trimmer P1, the magnitudes at both TP3 and TP4 will be changed simultaneously. At stage 4, the input signal enters from the port E of the trimmer and it exits from port S of the trimmer. The trimmer P2 is used to control the volume, which allows the user to adjust to the desired level. At this stage, IC3 uses an LM386N1 op-amp, which is a low-voltage audio power amplifier. Since it is configured to work in a single supply mode, there is no need for a voltage divider to remove DC offset voltage for the AC signal. The power amplifier provides huge current gain and is initially set to 20 according to the datasheet. Capacitor C15 and resistor R17 acts as a Zobel network, which helps in the stabilization of the impedance of the speaker at high frequencies. The inductance that was already present inside the speaker causes its impedance to increase at high frequencies. At that point, the power amplifier's efficiency will be affected. By establishing a parallel impedance link to the speaker's inductance, the Zobel network accounts for the rising impedance and produces a more stable load impedance at high frequencies. This keeps the voltage stable at high frequencies and ensures the power amplifier runs well. Finally, capacitor C13 filters the output signal and serves as a coupling capacitor, allowing only AC to pass through while blocking any DC voltage. The large capacitance of capacitor C13, which is 220 microfarads, helps to maintain a minimal gain when a low-frequency AC signal is sent into the speaker. To set up stage 4, use the same function gen and power supply. For the oscilloscope connections, connect channel 1 probe to TP4 and channel 2 probe to TP5, and both black clips to the ground of the breadboard. Switch on the power supply and function gen. We can see that by adjusting trimmer P2, we can control the output signal at TP5. The maximum output achievable results in saturation, which is 8.32 volt peak to peak. By adjusting trimmer P1, we can also control both outputs at TP4 and TP5, as both depend on the output of stage 2. Now, I'll be sharing on how I could improve the design. We could connect a ceramic capacitor and an electrolytic capacitor in parallel near the power supply connections. For example, 0.1 microfarad ceramic capacitor and 10 microfarad electrolytic capacitor. Each should be connected in parallel for efficiency in filtering capability. Also, connecting in parallel means the total capacitance increases, which provides better filtering. By using these two capacitors, it can effectively filter out noise across a frequency spectrum. The ceramic capacitors handle high frequencies, while the electrolytic capacitors can manage low to medium frequencies. All in all, they maintain constant voltage rating, which ensures reliable operation in power supply, decoupling, and filtering applications. After I patched the circuit, I used various troubleshooting methods. Firstly, I examine the circuit and then see if there are any damages to the components. Most importantly, I look out for loose connections visually. After that, I break down the circuit into 4 sections and check if I can get the desired output waveforms. When I checked with each test point, I couldn't get any waveform from TP1 to TP2. I could only get one straight line for both my input and output waveform. Then, when I visually inspected the circuit and my connections again, I realized that capacitor C2 and resistor R2 are connected separately in parallel instead of series. After I connected it in parallel, I got my desired waveform and output voltage. Moving on to stage 2, there was nothing wrong as I could change the voltage gain by adjusting the trimmer P1. Next, at stage 3, I was supposed to get a correct output and the unity gain, and the two waveforms of output and input must be the same. However, I couldn't get it. I found out that the function generator must be at the input at stage 1 even if moving to different stages. Because I have been moving my function gen input around, I couldn't get a correct waveform. After fixing that, I was able to get a correct waveform. Lastly, at TP4, there was nothing wrong as I could adjust the output sine wave at TP5 by adjusting the trimmer P2. It is served for the volume control, and by adjusting trimmer P1, I could change both waveforms at TP4 and TP5. With that, my circuit is fully working.